Yeah, so welcome back, everyone, to our first panel discussion on the very popular topic of what is quantum field theory. So the way this will work is that each of our two panelists will give some brief remarks, maybe about 10 minutes each, and then we'll turn things over to the audience for discussion. Yeah, maybe, I mean, the time is flexible. We very much hope for audience participation, so we'd be very happy to hear all of your perspectives on the topic. Before we start, I'd like to say a few words about our two panelists for today. So Dan Fried is a professor in the mathematics department here at UT, and Shu-Heng Shao is a professor in the physics department at Stony Brook University. Both of our panelists have the common property that their work is extremely broad and has spanned topics not only in high energy and low energy physics, but also in mathematics. So specifically, to paraphrase his own words, Dan has worked on various problems involving global issues in geometry and global analysis, and his work often relates to questions in theoretical physics, including quantum field theory, string theory, and condensed matter theory. Likewise, to paraphrase his own words, Shu-Heng has a broad range of interests in quantum field theory and its applications to condensed matter systems and quantum gravity. He has worked on a diverse set of topics, including symmetry, anomalies, and defects. We look forward to hearing both of their thoughts on quantum field theory. And Dan, if you're ready, please go ahead.
Sure. Well, thank you, Yale, and thanks to the other organizers, for the invitation to speak. So if I were giving the short version of this presentation, the answer would be simply, I don't know, but I will give a longer version. So I will try to give a longer version. It was working before. Oh, why is it not? Okay, we'll get it to change somehow. So we'll start with the meta question of what is what is. What does it mean? It's a serious question. What does it mean to say what something is? And so my favorite example is the real numbers. What is the set of real numbers? What is that? And it's captured by three words: a complete ordered field. And in this case, the real numbers are unique. And this is really the first main theorem in an undergraduate course on analysis, that the real numbers are the unique complete ordered field. So that's an existence and uniqueness statement. And the existence is proved typically by one of two methods: by constructing real numbers as Cauchy sequences of rational numbers, or through Dedekind cuts in the rational numbers. But notice that in the statement of the theorem, there are no infinite decimals, there are no Cauchy sequences, there are no Dedekind cuts. There's nothing familiar about what we use in real numbers. And in fact, if we think about real numbers as, for example, limits of Cauchy sequences, really equivalence classes of Cauchy sequences, then imagine the pain of just adding two real numbers, much less trying to do calculus. So it was a real intellectual kind of advance to frame this idea of what the real numbers are as a complete ordered field. That was historically kind of hard fought, hard won, and it had many consequences. And as I say now in an undergraduate class, in a semester, we teach some of the consequences that flow from that definition. So, yeah. Now, usually we're talking about a class of objects where it's not unique, like as the real numbers are unique. For example, a smooth manifold, or in this case, a quantum field theory. And so what we try to do is axiomatize its key features. Again, describe what it is by, in this case, not characterizing it uniquely, but describing its key features. That may not be a description of how we construct them. So it's neither a construction nor a classification, but it allows us to recognize what this structure is, and in particular, to recognize that structure in new situations or find new examples. That's really an important function, an important part of mathematics, in addition to problem solving and all sorts of other things, is the conceptualization of structure. And once we have different structures, then there are lots of marriages that go on. So for example, between the abstract structure of a group, another historically hard-won concept, and the structure, say, of a smooth manifold, we get a Lie group. If we marry those, if we marry it to an algebraic variety, we get to a scheme, we get an algebraic group, et cetera, et cetera. So these conceptualizations of structure come from examples, but they again lead to new examples, and that's their power. So that's a little bit, but in a sense, the most important slide about what it means to answer the question, what is? All right, so now let's turn to quantum field theory, but we'll start with quantum theory. And as I said, we want to axiomatize key features. And so let's look back at axiomatizations of quantum theory. This is from the very early days of quantum mechanics, really. Von Neumann was very much involved in the late 20s and early 30s with the development of quantum mechanics. And simultaneously, of course, von Neumann was a great mathematician of his day. And Dirac, too, really had a wonderful mathematical sense, I would say. And so they wrote axiom systems for quantum mechanics in these various books. The book by George Mackey is a wonderful book as well, in terms of states and observables and various properties. And there's a second kind of axiomatization, which is also due to von Neumann and Irving Siegel. We'll encounter a different Siegel later. And notice that he says here that only the observables occur and not the states in this description in terms of more algebraic, in terms of algebras of observables. The kind of algebras, by the way, that von Neumann and his collaborators especially were developing in mathematics at the same time. So I loosely think of these as the Schrödinger and Heisenberg viewpoints, the focus on states in a sense, and the focus on observables. Okay, when we come to quantum field theory in Minkowski space-time, then there are two corresponding kinds of axiom systems. The first one is the Whiteman axioms, which are listed here. And the second one, which focuses more on the operators, is due to Haag and Kostler. And you get a flavor for it here. And again, these are not, I'm not saying these as if these are complete descriptions of every quantum field theory one is interested in flat space. Of course not. One, and we'll hear from Shu-Heng especially, how the notion of a quantum field theory is being extended. But nonetheless, these are the traditional kinds of axiomatizations. So when it comes to quantum field theory, a kind of modern geometric view, then there are again two corresponding axiom systems. The one that corresponds to the Heisenberg point of view, so the Haag-Kostler kind of point of view, is due to Kevin Costello and Owen William, and there are 3 books that describe that. And this is again emphasizing, so to speak, algebras of operators. But they're no longer algebras, they're more complicated structure, factorization algebras. And I want to emphasize this is in the Wick rotated. This is axiomatizing what a Wick rotated field theory would be, not on flat Euclidean space, but on a curved manifold. And I'll focus on the other one, which is again more in line with the focus on states, if you like, or both really states and observables, and that's due to Graham Siegel from the mid to late 1980s, where he first introduced it in the context of two-dimensional conformal field theory. And very quickly, Atiyah adapted that to the topological field theories in all dimensions. But I think we know now that really this kind of point of view applies in general in quantum field theory. So let me say a word about what these axioms are. So again, just as other conceptualizations of structure that I mentioned in the first slide opened up new pathways into the topic, this also opened up new pathways, particularly allowed mathematicians to get into the game of studying various quantum field theories. So an analogy that's limited, but good to keep in mind in some sense, is to think of a quantum field theory as analogous to a linear representation of a group, or you might think of it as a module over an algebra, if you like. So what plays the role of a group here is a category of Bordisms, a category of manifolds. So it's not a group in the sense that the arrows in the category are invertible. That's not true. So in that sense, it's a little more like an algebra than a group. In any case, the objects here are n-1 manifolds, closed manifolds of dimension n-1, and a map from one such manifold y0 to another manifold y1 is a Bordism. That is to say, it's a compact manifold of dimension n, whose boundary is partitioned into an incoming part, which is equipped with a diffeomorphism to y0, and an outgoing part, which is equipped with a diffeomorphism to y1. And these compose by gluing, and that's the basic structure. So we have a discrete parameter that's telling us about the theory. That parameter is this dimension n. That's part of the description of what this domain is of a field theory, this Bordism category of n-dimensional manifolds. But there's the second discrete parameter, which is a choice of what are called background fields. So we might, for example, have these manifolds equipped with a Riemannian metric. So that's the usual case in quantum field theory, the Wick-rotated version, and then put on a curved manifold, a la Elie Cartan, of the flat Lorentz metric. We might have a connection for some group. We might have a B field, higher versions of those kinds of things. We might have spin structures, orientations, topological background fields, anything which is local. So there's a formal definition, which I won't give here. But telling what a field theory is, we have to tell both the dimension and this specifications of background fields. The same way, if I tell you what kinds of groups I'm studying, I don't just say I'm studying an 8-dimensional Lie group. I might tell you if it's SU3 or SU2. I might actually tell you a little bit more than the dimension. So that's the domain. And what's the codomain? Where do I map it to? Something linear. Well, if we're just doing this two-tier system of n-1 and n manifolds, we'll map to vector spaces. So in other words, every n-1 manifold here gets mapped to a vector space, and every Bordism gets mapped to a linear map between the vector spaces. But these vector spaces are infinite dimensional typically, and they should be topological vector spaces. So field theory is such a map. It has to take compositions to compositions, and there's also another structure, a composition law, on the objects and the morphisms, which is disjoint union over here and tensor product over here. So it's very characteristic in quantum theory that disjoint unions, the kind of conjunction of two systems, goes over to the tensor product. Classical system, it would behave differently. Okay, so again, this axiom system really is meant to apply for general quantum field theories, but it's certainly these ideas are most developed in the case of topological field theories and then conformal field theories. Okay, so there's an extension of this notion where we consider, for example, in a two-dimensional theory, not just 1- and 2-dimensional manifolds, but also 0-dimensional manifolds. And that means the two-dimensional manifolds have not just boundaries, and there are Bordisms between one manifolds, but also corners to incorporate the 0 manifolds. But I see that my time is already. So so one wants to have a higher notion of categories. There are more composition laws with these corners. And so we need to know what's the linear kind of place we map to that generalizes vector spaces. And in mathematics, there are a lot of different choices, and those are very useful. One could ask, is there some kind of universal appropriate choice for physics? So once we put in these corners and we're allowed to glue, this is really encoding locality. So again, axiom systems are meant to encode essential properties of whatever object we're axiomatizing. And here, these axioms really do encode locality in a very strong form. They don't, however, include unitarity. And that's good. You see, the idea of a representation of a Lie group also doesn't include unitarity. That's a separate structure we might ask about on a representation. When we study non-compact finite dimensional Lie groups like SL2R, then in the collection of representations, some are unitarizable, others are not. Well, it's the same in quantum field theory. Sometimes theories are unitarizable or indeed unitary, sometimes they're not. And so one needs to know how to incorporate unitarity in this Wick rotated way, but in a strong form that realizes this extended locality. Maybe I'll skip some of these. Just to say that this idea of an extended field theory was explained very nicely by Kapustin in his ICM talk. Maybe it was 2000, I've already forgotten. How that's related to the idea of higher dimensional defects in quantum field theory. So as I said, the theory is most developed in the case of topological field theories, and the central theorem, called the cobordism hypothesis theorem, is quite powerful. Okay, so going back to the what is question, how do we know if we have an axiom system that we've captured some essential properties of the thing we're trying to axiomatize? Well, we could try to measure the impact of this axiom system. As I said, it should lead to new examples, it should lead to theorems, and having conceptualized the structure in this way. And in mathematics, there are lots of things we can point to in low dimensional topology, in symplectic topology, in algebraic geometry, geometric representation theory, higher algebra, and number theory as well, where this kind of axiom system and this point of view on quantum field theory has had an effect on different things in mathematics. I would argue also that it's had an effect in physics. You can see certainly the influence of these axioms in the studies of defects, boundary theories being an example, in the ideas about invertible field theories, which are related to stable homotopy theory, that led to some classifications, which are relevant, for example, in condensed matter, also in the study of anomalies. There are classifications in the non-invertible case of topological field theories, which again, have an impact in classifying certain phases of matter. And there are new classes of examples of field theories, some that you might consider as a toy example, but they actually occur as parts of more realistic field theories, or as auxiliary objects, for example, describing symmetry in studying those field theories. And in the study of symmetry and anomalies, you can see the influence of these axiom systems. So I think, the one of Siegel has been around, as I said, since, it's well over 30 years now, and you can start to measure its influence. But I don't want to say that that's the last word and we understand what quantum field theory is. As I told you, the short version of the talk is, I don't know. And there are many kinds of questions. One is to develop the relation between these two kinds of axiom systems, just as there are in the other cases in Minkowski spacetime and also for quantum mechanics, as I said. The analytic aspects are definitely underdeveloped. So when we get away from topological theories and conformal theories, there's RG flow and everything else that needs to be developed. This idea of an extended QFT needs to be developed, again, in the non-topological case, as I said, unitarity. But maybe the main thing is examples. So to fit examples into this framework, to construct them, just as you construct real numbers by Dedekind cuts or by Cauchy sequences, those kinds of things are, there's a gap between these theoretical ideas and the examples. So again, we can do examples that are finite, discrete, semi-simple, those kinds of examples, but realistic systems, we need to make more contact with the other methods of constructing. All right. So in summary, our best answer, I think, are these kinds of axiom systems, just as I would say our best answer for what is quantum mechanics are the axiom systems of von Neumann, Dirac, and Siegel, and so on. But it's still early days. One needs to synthesize the ones in flat space emphasize some analytic ideas. And one needs those analytic ideas to be synthesized into these geometric and algebraic advances in the Wick rotated context. Okay, and we need more examples, as I said. So I'll stop there. Shu-Heng, take over.
Thanks a lot, Dan.
Oh, sorry.
Give me a few seconds to set up everything. Here's my Zoom. It's here. Share screen. Okay, well, yeah, so I would first also like to thank the organizers and also thank Yale for inviting me to participate in this panel discussion on what is QFT. And honestly, I feel totally unequipped and even terrified to talk about this topic because I really don't know the answer. So unlike an ordinary seminar where I usually talk about what I do know, here I'm going to talk about what I don't know. And since this is a discussion about quantum field theory, I hope everyone can allow me to use a more high energy physics language. In particular, throughout the talk, whenever I say dimension, I always refer to the space-time dimensions, not just the space. My discussion, unlike Dan's discussion, my discussion will not be rigorous mathematically. I will also omit a lot of adjectives in front of various TQFT or QFT. I will not be careful about the choice of the tangential structure. I will follow a slightly different perspective as suggested by Yale. I will approach this question from the point of view of generalized global symmetries. And at the end of the discussion, I hope there are more questions asked than answered. So instead of answering this big question about what is QFT, let me break it down into something smaller. What does a QFT person do every day? And what are the observables a QFT person would deal with? And perhaps more importantly, what specifies a QFT? One basic set of observables in studying quantum field theory is a spectrum of local or point operators. I know Dan used the term local differently than I do. Here I really mean operators whose insertion is a point in Euclidean space-time, and it doesn't depend on additional data. And we also compute various correlation functions of local operators on a general manifold. In 1+1D, we know many examples of rational conformal field theories where the local operator data are completely solved, such as the Ising conformal field theory. Another set of observables that we usually learn in our first few classes of quantum field theories are the scattering amplitudes of asymptotic states, which are directly relevant to phenomenology. But clearly, this cannot be the whole story for general quantum field theory in general space-times. Indeed, there are interesting quantum field theories with trivial local operator data and no asymptotic state. One famous class of examples are the trans-Simons gauge theories, where without matter, where there's no local operator at all, except for the identity, and there's no asymptotic state. And yet it's a very interesting quantum field theory that's relevant to knot theory and to topological order. So more generally, to specify a quantum field theory, we cannot just focus on the asymptotic states and the local operators. We have to also consider the extended operators and defects. Now, for the bulk of the talk, I will only talk about relativistic quantum field theory. So I'll use the word operator and defects rather interchangeably. So for example, the extended defects I have in mind include the Wilson lines, the 't Hooft lines, the Hukov-Witten operators, and many others. And there are many examples of different quantum field theories sharing the same set of local operator data, but distinct set of extended defects, such as the SU2 versus the SO3 gauge theories. So we really have to confront with this additional, more refined data in a quantum field theory. So in order to specify a quantum field theory in these space-time dimensions, what do we have to do? Do we need to know all the k-dimensional extended defects with k less than d. That seems a little bit overly ambitious and seems pretty wild. The reason is because given a k-dimensional defect in a d-dimensional quantum field theory, we always have the freedom of stacking or coupling a decoupled k-dimensional quantum field theory on top of that defect that we are given. So for example, you can couple 1 plus 1D Ising model to the 3 plus 1D standard model, and that creates a surface defect for you. So classifying all the k-dimensional defects in a given d-dimensional quantum field theory appears to be at least as difficult as classifying all k-dimensional quantum field theory. And this freedom is not unrelated to those of you who are familiar with the couple layer construction for fractons and also the foliated fractal folder. And the similar comments apply to boundary condition as well. One can try to define certain equivalence classes of defects or boundary condition as follows. We can say that two defects, D1 and D2, are equivalent to each other if they differ by stacking a decoupled k-dimensional quantum field theory Q. However, as written, this is not the equivalence relation in the mathematical sense, because it could be that D1 is equivalent to D2 and D2 is equivalent to D3, but 1 and 3 are actually not equivalent. And this basically follows from the fact that quantum field theory in general are non-invertible. And the similar comments apply to boundary conditions as well. We can add some adjectives to make our lives slightly easier. We can say, let's just try to classify all topological defects in a given relativistic quantum field theory. In a relativistic quantum field theory, topological defects are nowadays viewed as synonyms to generalized global symmetries. So the question now becomes, can we classify all generalized global symmetries in a given fixed quantum field theory? The question is still very difficult, but slightly under better control, because the freedom that we had in the earlier slide of stacking or coupling a decoupled quantum field theory now becomes the freedom of stacking or coupling a decoupled TQFT. And the space of TQFT is better understood, but still generally an extremely difficult question. So let's start with topological lines in a given quantum field theory in general dimensions. Let's say I start with a topological line L, and now I'm going to entertain with the freedom of stacking that topological line with an additional decoupled 0 plus 1D TQFT. Now, what is a 0 plus 1D, I should say, bosonic TQFT? Well, it's just a free qubit. It's topological, so the Hamiltonian has to be trivial. So you just have a finite n-dimensional Hilbert space, and there's nothing else. Hence, the stacking of this decoupled 0 plus 1D TQFT with the given topological line in this given quantum field theory, just multiply the line by n times. So this freedom that was bugging us in the previous slide is not that severe for topological lines. It just gives you a multiplicity, a Chen-Payton factor, if you wish. So in that sense, the space of topological lines in a given QFT is under better control. And indeed, we have several examples where we think we have a good understanding on what are all the topological lines in a given quantum field theory. For example, we talk about the Wilson lines in a given Chern-Simons theories in 2 plus 1D. Similarly, the space of 0 plus 1D topological and even conformal boundary conditions of 1 plus 1D QFT is under better control. Examples include Cardy's boundary state for 1 plus 1D rational conformal field theory. Moving on to topological surface defects, then things become slightly more non-trivial. But still, the space of 1 plus 1D TQFT is relatively well understood. It's related to the fact that there's no long-range topological order in 1 plus 1D. So when you couple a non-trivial 1 plus 1D TQFT with a surface defect, that will give you something not simple, namely that it's decomposed into several other surfaces. But there's still more subtle data that I will not talk about then. The thing I would like to emphasize is that once we go to 2 plus 1D topological defects in a general QFT of diverse dimensions, then the freedom is really wild. We have the freedom of just stacking or coupling a decoupled 2 plus 1D TQFT on top of this 2 plus 1D topological defects. And we all know the space of 2 plus 1D TQFT is extremely rich, including all the Chern-Simons gauge theory and other TQFTs. So the question is, how do we actually organize all 2 plus 1D topological defects in a given 3 plus 1D QFT? And as I said, topological defects are nowadays viewed as synonyms to generalized global symmetries. So one particular question one can ask is, what are all the generalized global symmetries of our QED? And here I really mean our QED, not QED in 2 plus 1D, not QED with supersymmetry, just one of the few first quantum field theory we learn in any quantum field theory course. This seems like a question that Feynman or Schwinger or Dyson might have completely answered more than half a century ago, but it's actually much more subtle and richer. And similar comments applies to classifying topological boundary conditions in higher dimensional TQFT. So I'm almost running out of time, so let me just summarize. So clearly the local operator data for quantum field theory are not enough to unambiguously specify a quantum field theory. And we also have to think about extended operators and data. But once we think about them, it seems completely wild. And I would like to recommend you this very nice lectures by Dan at Perimeter just a few months ago, trying to approach a similar related question from a more rigorous mathematical approach. And everything I said so far in this talk, in this presentations, are about standard relativistic quantum field theory. And for non-standard quantum field theory, the corresponding question is only even more difficult. Just to name a few, what about quantum field theory for fractons? What about log CFT, TT bar deformed CFT, or even celestial CFT and Lipschitz theory? So I'll end my talk here. And as I said, I don't think I answered anything. So I just want to add 2 more question marks to the original title. Thank you.
Thanks a lot, Shu-Heng. Let's turn things over to the audience for either questions or comments. And this includes either the in-person audience or the Zoom audience. If you're in person, please wait for the microphone. Thank you.
Is it true that for relativistic systems, those systems with generalized symmetries are not violating any traditional axioms that Dan introduced?
Question for Dan. I will let Dan answer first.
The question was, do the standard relativistic systems satisfy the kinds of axiom systems I said? That's the question.
The relativistic systems, but with generalized symmetries that Shu-Heng described.
Oh, I see. Well, yes, I think they should satisfy those kinds of axiom systems. I mean, the question of symmetry is a little bit different, perhaps, than the question of the theory. We could think about, for example, if I think about a round 2-dimensional sphere, that falls under what is a manifold and so on, whether or not I think about all the rotational symmetries of the sphere. If I'm asking what kind of object is the sphere, I don't have to think about its symmetries. I could ask separately, what does it mean to have a symmetry of a sphere? What is the collection of symmetries and so on? So similarly, if I had a relativistic quantum field theory and I wick rotate, which is the context for those axiom systems I was talking about, then hopefully we can fit them into those axiom systems. As I say, that's at an early stage to think about theories that are not scale invariant, so neither topological nor conformal. But nonetheless, I think we'd like to think that they fit into some version of the axioms that might have to be refined. For example, to capture the idea that at short distance, the theory is well behaved. So it has some kind of limit, in the ultraviolet, so to speak. The question of symmetry and what symmetries are is another one that's undergoing, I think, rapid development. And then we could apply those to that kind of theory or to topological theories or what have you.
Not much to add. But if I understand correctly, that's one of the goals in the series of lectures you gave at PI, right? Trying to incorporate finite symmetries and more generalized symmetries into this more axiomatic and rigorous formalism of quantum field theory.
Well, I wouldn't say rigor was the goal, but I would say conceptualization, let's say, at this stage. And the key idea there is a very simple one, which is, again, mathematically and historically, an important notion was separating concrete symmetries, like the symmetries of a pine cone, the symmetries of the roots of a polynomial equation, and understanding that there's a commonality there in the structure of an abstract group, or then the structure of an abstract algebra. And eventually, if you're studying symmetries of Lie groups, linear representations, you end up studying, for example, the modules over the universal enveloping algebra. So seeing how those work together. And so those lectures are the starting point for those, which were based on discussions and a paper coming out with Konstantin Telemann and Greg Moore, is to say, well, what is this abstract structure of a symmetry in quantum field theory, this kind of symmetry, including these global categorical, non-invertible, whatever words you want to use. And can we understand that, the abstract group, and then can we understand what it means to have a module, what it means to have it acting on a quantum field theory. And we were studying the ones that are analogous to finite groups as a starting point, where the abstract symmetry is itself a topological field theory. So we have a lot of foundation for studying that. And the analog of like an element of the universal enveloping algebra is a defect inside this topological field theory. And so then we could say that the topological field theory acts, so to speak, that an ordinary theory, whether it be four-dimensional QED or whether it be some other theory, could sit as a module for this, and then we could separate out and use techniques of topological field theory to study those symmetries and perhaps learn something about how they act.
I have a question for both of you. So in field theory, it sometimes happens that, oh, okay, we have one time direction, but then it's useful to consider Euclidean like a purely space version of the conformal field theory. And my question is whether it's also sometimes useful to consider field theory or maybe axiomatize field theory with more than one time direction. Is it useful at all?
Yeah, I should repeat the. Do I only for people on Zoom?
It's okay. We heard the question.
Okay. Let me try to give one example. I think that's super useful, but I wouldn't say it's two time direction at the same time, right? It's more like you start with a Euclidean configuration and you treat, you pick two different directions as time in two different setups and trying to make sense of both calculations. As the famous example is the modular invariance argument, or maybe Cardy's classification of boundary states in rational conformal field theory. You start with a Euclidean configuration. You have two directions in your 1+1 in your two-dimensional manifold. You can pick one direction as the time. It has one Hilbert space interpretation. You can pick the other as time that has a different Hilbert space interpretation. Both have to make sense, and that gives very strong constraints on quantum field theory. And I think there are many such examples where a Hilbert space interpretation becomes important when you pick a particular time direction in your Euclidean space-time.
Well, I don't think I really have much to add there. I think when you're looking at quantum field theory Wick rotated in Euclidean signature, then there is no time, so to speak. But there are theorems about Wick rotating back and deducing things about the relativistic. So in the context of Whiteman field theory, for example, there's the Osterwalder-Schroeder theorem, there's the CPT theorem, in a sense about that, and so on. But that all is Wick rotated back to one time, to Lorentz signature. And I'll just say that I've always found a compelling kind of algebraic fact about Lorentz signature that distinguishes it, having one plus and the rest minus, or vice versa, from any other signature, which is the following algebraic fact, that if you take a real representation of the spin group in a signature, you can look at the symmetric square of that representation. So that's exactly the kind of thing you would look for to write down the kinetic term for a spinor field. So the kinetic term is written down with a symbol gamma mu ij or something, where the I and the j are the spinor indices, and that's symmetric, and the mu is the vector. And the theorem is that inside the symmetric square of a real spinor representation, in Lorentz signature, you can always find a copy of the vector representation, but that's the only signature in which that's true. So if you wanted to try to replicate what one does with spinor fields, at least in Lorentz signature, that algebraic fact might be an impediment if you tried it in a different signature.
Well, let's take a question from the Zoom audience. So maybe we can alternate between in-person and virtual questions. So Xiaogang Wen has a question. Please go ahead.
Yeah, it's a question for Dan. You mentioned about this cobordism, and you can add a structure to the manifold. I kind of wonder, what if you add like a Riemann, this metric structure, or maybe Taylor structure, this complex.
Sorry, I didn't. Which structures did you said two of them? I didn't catch.
It's a Riemannian structure. It's a metric structure. So can metric manifold. That's the one structure.
Metric.
Yeah, this is a GIJ metric, some kind of
A Riemannian metric.
Riemannian metric. Yeah.
Okay.
Another structure I have in mind is like a Taylor, like complex manifold. I wonder whether there's some idea. So what this, if you're adding these two, what you'll get in the quantum field theory?
Well, I think if one were to study, for example, four-dimensional QED, then it would be on a, functor out of a Bordism category of Riemannian manifolds. I mean, that would be exactly the kind of background field that you would have. Yeah, so that's definitely in the ball game, I would say.
But if you have a complex structure, also, whether you get something, whether there's some idea what one might get if you have a complex structure, in addition to Riemannian structure.
Well, maybe I should say the initial notion of the idea of topological twisting is introduced by Witten in the late 80s, was to twist the theory to where you could put it on an arbitrary smooth manifold, maybe with some extra orientation or structures like that. But there are also twistings that have particularly been exploited by Kevin Costello and his collaborators about where you twist, and in some directions it might be topological, in others it might be complex. So you would have a manifold that might have a foliation, where on that foliation you have a complex or something like that. So I think there are examples out there where indeed complex structures also appear.
So somewhat related to Xiaogang's question, given that Wick rotated Euclidean spacetimes are sort of built into the axiomatic definition of a QFT, to what extent is that an implicit assumption of relativity? For example, in condensed matter systems like quantum Hall, you often want to define QFTs on Newton-Cartan spacetimes instead. Would those fit into this framework, or would the axioms have to be expanded for that?
You want to go first?
Oh, okay. Sorry. First, let me also add that for the for Xiaogang's question, for the holomorphic twist, there are many other examples earlier than Kevin's work, like Leonardo Rastelli and collaborators. They have some holomorphic twists for four-dimensional supersymmetric theories. But for the other question, is the question about how important is relativity or relativistic symmetry? or how is that incorporated in the system?
Is it implicitly assumed in the current axioms or not?
Oh, I see. I think it's an input, right? Then correct me if I'm wrong. But the onside of all these axioms is that you start with a quantum field theory with certain symmetry. It could be topological, then you don't have to talk about metric at all. Or it could be just some relativistic quantum field theory, then you can put it on a general Riemannian surface, Riemannian manifold, and the answer will depend on the choice of the metric. Or, there could, as you said, there are many condensed matter systems where the low energy description might not have the relativistic symmetry. Then when you try to put it on a general space-time, then you have more restrictions or different choices of the tangential structure you have to assign to the kind of manifold you want to work with.
So that would be additional data on top of these axioms.
Yeah, I think that's always some assumptions or some background data you have to assume. I think the background is the exact word that Dan like to use.
Let's take a question from Zoom. John McGreevy has a question.
Yeah, hi, thanks. I wanted to ask a question based on something that Dan said, which is what is the implication of the cobordism hypothesis or theorem or whatever it should be called for the classification of, I guess, gap liquid phases in various dimensions higher than 2+1?
Well, I'm not sure what the word liquid means. If you want to expand on that.
I don't want to talk about fractons.
Oh, I see. Well, okay. So, I mean, there's a lore, I don't know, what do you call it? Some kind of statement, a folklore statement that if you have a gap system, well, first of all, that a field theory is, or any quantum system, I should say, is described at long distance or low energy, if it's relativistic, by a scale invariant quantum field theory. Then you might hope that that quantum field theory is conformally invariant. And furthermore, if your quantum system is gapped, then that quantum field theory is, perhaps up to an invertible theory, is topological. And that furthermore, any long distance kind of question, like the phase that you might ask, should be captured by that approximation, which is essentially a topological field theory. So when you start asking those questions, then you can bring to bear the cobordism hypothesis, which is telling you, something about the space of topological field theories of a given type. You can bring that to bear on those kinds of questions, on classification question of phases. So if you're imagining a moduli space, a moduli stack even of theories, then the question of phases is typically the question of pi naught, of path components. So you say two systems are in the same phase if they can be connected by a smooth path in this kind of space of gap systems. So that's a question you might be able to answer from the cobordism hypothesis, because it gives you a description of the homotopy type of that space of theories, these low energy approximations. And so you could calculate pi naught of that homotopy type. You might ask more subtle questions that would detect higher homotopy groups, some kind of path of systems and so on. I don't know if that answered the question.
Well, I guess the thing I was hoping to learn was, does it say, for example, that we know all of the topological field theories in 3+1 dimensions? Are they just Digraph-Witten theories, or say unitary topological field theories?
Well, yeah. So all those adjectives are important to know. So, the way I said it, a field theory has a domain, which is this Bordism category, and it has a codomain. And any question you're going to ask might depend sensitively on your choice for that domain and your choice for that codomain. So to pose a precise question, we really have to say that. So the domain, as I said, is a matter of saying what dimension the theory is, but also these background fields, whether it involves an orientation or a spin structure. These are topological examples of background fields. And, so for some choices of that, well, the cobordism hypothesis gives you a way in terms of the codomain to potentially to describe that space. It's a very strong step. But now you have essentially an algebra problem algebra and topology problem in the codomain to solve. And so, you'd have to then dig into specifically what the question is to see how much you could say about that problem. But it gives you a framework for attacking them all. It gives you a uniform framework.
I don't see any questions in the room yet. So maybe
Good. Good. So we have another Zoom question from Nadi Cyberg. Please go ahead.
So before I start, I have a comment. I think that these two presentations were absolutely superb. I enjoyed every second of it.
Thank you.
But there's something that bothers me, and it's not in the present. Does not bother me in the presentations. But can you repeat this snide remark?
Pardon?
Okay, I thought there was a snide remark. There's something that bothers me in this question in general. There's something that I've lost a lot of sleep over. And this is the role of the renormalization group. And I was really struck that none of you mentioned the renormalization group. The word universality did not appear in the two presentations. The way I like to think about that is that you think about the whole quantum field theory as a whole package, including the UV and including the IR and the flow between them. But historically, we know that although this is correct, it really hides a lot of interesting information. And at least in the 70s, there was this breakthrough of Wilson and others that you formulate the theory in the UV and you try to understand what happens at long distances in the IR. And Dan's formulation or Dan's presentation of various formulation includes that, of course, because you can look at short distances and long distances. But the separation that you can take this separation between UV and IR was not central in the presentation. So maybe this whole thing from the 70s is a red herring, and in future presentations of quantum field theory, there will not be any separation of scales, and we just study the whole thing as a package. My hunch is that the thing from the 70s will be central, and the theory is formulated in the UV, and the way we think about it is that the UV is the question and the IR is the answer. And I'm really struck that these keywords, renormalization group, Wilson, universality, and since you're in Texas, I would also add the name Weinberg in that context. None of that appeared in these two presentations.
Yeah, for me, there's a good reason because I thought you are going to talk about it on Thursday.
I'm not. Do you want me to talk about it?
I thought you were going to talk about some, fractons and how UV and IR might mix. Even have a peek about some of your slides. So, okay, maybe I misunderstood it.
I will say a few words about that. Yeah, I will say some words about it, but I think the surprise when they mix, and the reason you both stayed away from fractals in your presentations, the reason is, what this is really telling us is that the separation of UV and IR is central in the regular case. And if it had not been central, you would not have stayed away from fractals and you would not be late to me. So I think first we need to understand it, how it fits in the regular framework. And I'm really missing the fact that it's not so central in these two presentations. I don't have anything to offer, but it's just something that has been bothering me.
Well, thanks, Nati. That's, of course, an excellent point. And I'm sorry I'll miss your presentation on Thursday. So I actually did put the renormalization group on one of the slides, and it was the slide of open questions, where I was particularly trying to emphasize the importance of incorporating analytic ideas into the framework. So, I would say that a lot of the advances in understanding, and certainly the applications to mathematics of this framework, have been algebraic and topological, and in that emphasis, and not much in the analytic way, which is where the renormalization group certainly fits. And so I definitely think we need to incorporate that. I mean, it's clearly in the formalism, just as a formal idea, namely if you have a Bordism category of Riemannian manifolds, there's a one parameter semigroup where you just uniformly scale all the metrics. And that, you compose your theory with that. That's the renormalization group flow. It gives you a flow of theories. But that's just a formal statement. And if we think about what would correspond to a more classical kind of physics, namely PDE, I mean, think about the Navier-Stokes equation, or think about lots of other evolution equations, wave equations, and so on. In PDE, as you say, the question is the short distance. So the question is, you write down the PDE, are there solutions for short time, the short time existence? That was, for example, in Ricci flow, one of the first theorems in the subject of Hamilton, that we have short time Ricci flow. So that's the well-posedness. That's analogous to saying that in the UV, your quantum field theory, maybe it's asymptotically free, or maybe it flows to some conformal field theory in the UV. That's a kind of well-posedness. And then the interesting questions in PDE are often the dynamical questions at long time or long distance, stability, singularities that you get. So in the Ricci flow, for example, you hit a singularity in the flow of, say, a 3 manifold, and then how do you continue past, and so on. So that's where all the interesting questions, the kind of answers, as you say, are. So I think we know that very well in PDE, in lots of different PDEs. And I think, as you taught me, it's the same in quantum field theory. So this framework is only meant to be a very formal answer to what is, but there have to be meat on the bones, theorems, in the sense of, well, you can construct such a thing by, for example, some kind of well-posedness, that maybe some kind of small Riemannian manifolds in some way, the theory makes sense. And then we can ask, does it extend to Riemannian manifolds that are larger? Do you run into singularities, that kind of thing? And those are the kinds of questions I think you're getting at. And I just, it's early days just trying to say what this beast is of a quantum field theory. But absolutely one needs to put in these kinds of analytic ideas to put meat on the theory.
Xiaogang Wen has a comment, perhaps.
No, I don't have. I just have a question. It's actually the follow-up of John's question. Is we have this definition of QFT. That's something like a fully extended, fully dualizable unitary QFT defined by this cobordism. And with this definition, do we have a classification, say, in a lower dimension, like in 2-dimensional space-time, 3-dimensional space-time, or 4-dimensional space-time? Maybe in 2-dimensional space-time, there's a fully extended dualizable, maybe hopefully it's trivial, that's we guess. And in 3-dimensional space-time, maybe relate to some kind of modular tensor category. But then whether in 4-dimensional space-time, do we have some known result from mathematical side? Yeah, that's for that, yeah.
Sorry, the question was, are there classification theorems in 4 dimensions?
Yeah, that's what John is, but we'll define this with all the adjectives, like a fully extended, some kind of, I don't know, fully dualizable, those kind of things, whether we have some mathematical results in this direction.
There are mathematical results in that direction. Again, you have to say what codomain, so you need some 4 category as the target of your field theory. And so if you take that codomain to be braided tensor categories, where what we mean more technically is E2 algebras in the suitable 2 category, then you're asking the question of what are the fully dualizable objects in that E2 algebras. And maybe then one would ask about some kind of invariance to do with the background fields. So there is some work of David Jordan and his collaborators, for example, about this kind of higher algebra, the dualizability, these kinds of finiteness conditions in that general context. So there are other people that I'm not telling you, but I mean, yes, so there is a community of kind of algebraically inclined people working on that kind of question, at least in that context of what would be braided tensor categories.
Yeah, let me try to translate a little bit. When you say codomain, you mentioned about this, do you mean some kind of category of vector space? But now maybe it's a higher category vector space, and that one have some uncertainty. So it's so that's maybe difficulty. If that's what you mean.
Yeah, I mean, if we have a four-dimensional theory on a closed four manifold, you would think we get a complex number, right?
Yeah, yeah.
Okay, and it's complex because of basic things in quantum mechanics, right?
Yeah.
Interference and so on, why it's complex. And to a three manifold, you get a complex vector space. Again, superposition dictating the linearity of a vector space. So you might try to take superposition and interference and say, okay, what do you get in codimension 2 on a two manifold? What kind of a thing should we get? Okay, we might give a nice answer for that. Well, what about in codimension 3 on a one manifold and so on? So we're going to get complicated algebraic objects, but there might be some freedom in choosing what they are, because you're not going to ask questions about really what is the whatever object you're computing on a one manifold. Ultimately, you're asking about numbers you compute, some correlation, you know, functions or scattering, whatever. So these are ways of kind of intermediate steps of factorizing your problem. That's the kind of, but nonetheless, you have to say what that is to start to solve the problem.
So somehow you say the physics somehow did not provide a non-ambiguous answer for what is a codomain and the structure of all those vector space or all the codimensions. So that's what makes things less well defined.
Well, do you think physics provides an unambiguous answer that in codimension 1 we get a complex vector space? Is that unambiguous?
Okay. Yeah, I think that one is I think people agree. Yeah, codimension complex vector space. But then in the low, you know, yeah, I see. In the higher codimension, things become very complicated. I don't know. Yeah. Thank you.
It's a little less unambiguous. But I mean, having said that, again, approaching it from a kind of mathematical structural mindset, you might specify some universal properties that you'd like. For example, we know what the invertible object should be. There's an answer for what that should look like. So that might be a specification you would require. And then you might want, of course, linearity, and maybe you don't want anything else. So you want the universal object. So there is actually recent progress, you know, kind of abstract progress about that kind of question as well.
Yeah. Okay, thank you.
I have more questions in the room here.
Okay, go ahead. Go ahead.
Yeah, thank you, Dan and Shu-Heng, for excellent presentation. So I have a question on what's the concrete connection and application of frameworks presented by both of you to say non-Lagrangian QFTs. Like, did they bring new examples or new results in classification?
I think one point of both of our presentation is that we don't want to work with the Lagrangian. So yeah, originally I had some comments about Lagrangian in the first slide, but I removed them later on. I mean, indeed, I think the goal of setting up a framework for quantum field theory in general is that we hope to achieve some kind of classification or organizing principle without having to use any Lagrangian.
Yeah, I mean, again, I would go back to separating out the axiomatization or conceptualization of a particular structure and the construction of examples. So if we take a course in group theory and we define a group and develop some elementary process properties, we never see a matrix. And so you could say, well, okay, I'm developing a group, but I don't see a matrix. But the groups I know, they're groups of matrices, you know. Well, that's a great way to construct examples, but then there are non-matrix groups as well. And so I think it's similar here, that we would try to say, what is a quantum field theory? And the Lagrangian won't be part of saying what that is. I'll point out that in the framework I'm saying, there are no fluctuating fields. They've, so to speak, been integrated out, and what's being axiomatized is the result of integrating out the fluctuating fields, where you only have the background fields left. But a Lagrangian would be important, of course, in constructing many examples and in studying the kind of analytic questions, renormalization group flow that Nati was asking about.
Well, okay, I still see, okay, go ahead. No, there are no Zoom questions right now.
Okay, I have a question for Dan. Yeah, this question is for Dan. Suppose we are interested in a formulation of a TQFT with a Bodism and a cobordism. Yeah, that formulation. So yeah, I have the following question. In that framework, it looks like the crucial object is some manifold which can be the boundary, actually be part of the boundary of a one higher dimensional manifold. Then my question is, in lower dimension, we understand that every orientable manifold can be the boundary of some one higher dimensional manifold, but in higher dimension, like maybe four dimension, yeah, there are manifold which is not the boundary of some one higher dimensional manifold. Are those manifolds special in some sense, in any sense, in that framework?
Oh, that's a very great question. Let me just point out that there are zero-dimensional manifolds, namely a point, which is not the boundary of a one higher dimensional compact manifold. It's, of course, the boundary of an infinite ray. And once we eliminate compactness, then that question goes away. But just if we want a compact manifold, we can't put a point as a boundary. Well, that fact has a ramification, an echo in the study of topological field theory. You might try for, so to speak, a cheap way of extending, say, Chern-Simons theory to a theory of 3, 2, 1, and 0 manifolds, but you reach the obstruction that a point doesn't bound a compact one manifold. And so, yes, so in a sense, you do run into that question internally, so to speak, in studying topological field theories. But conceptually, it just means that certain Bordisms won't occur, right? I mean, you can't have a Bordism from, say, a 5-dimensional Bordism from CP2 to the 4-sphere, right? That just doesn't exist. But that's okay, that doesn't obstruct. You know, in the same way, when we talk about background fields, we might talk about, say, spin structures. That's something local. We can define locally what it is. It's sheaf-like, we can patch them and so on. But globally, they may not exist. I mean, sheaves may not have global sections in general. And so if you're on the manifold RP2, you won't have a global spin structure. But it doesn't mean a spin structure isn't a good concept in field theory as a field. It's something local, and it's good. It's just that globally, things don't always exist. The question was, does that mean sometimes you may not be able to put a ground state on that manifold? Well, that means that if you're considering a 3-dimensional theory that requires a spin structure, you can't even ask the question in a sense, because that's not in the domain of the theory.
Hi, so this is kind of related to Nadi's question, I think. So like when I think about QFT, it's usually in the context of like theory space. And so, I mean, in the theory space of like quantum mechanical systems, you can have things like Berry phase. So the topology of the theory space depends or affects physics a lot. And so I think there's some work about this in the context of QFT, but I'm especially interested also in the perspective of this theory space idea for these functors which define the quantum field theories. So if you have any comments, that'd be very interesting.
Okay, well, let's see. So one thing to say is that the axioms I said were, you to an n-1 manifold, you attach a vector space. To a Bordism, you attach a linear map. But that's not enough. you need to be able to, for a family of n-1 manifolds, to attach a family of vector spaces, and to a family of Bordisms, you want to attach a family of those numbers. So for example, when you study correlation functions in a typical quantum field theory, they are functions, correlation functions, not correlation number, and they're functions of the points at which you insert those point operators. And so that's a family, you see, of Bordisms, if you like, where those points are moving around. So it's always important from the beginning to evaluate in families. Now that's internal to a single theory, but it's also important to have the notion of a family of theories, as you said. And there's a relation of that, and this is again an idea that Nati has exploited quite a bit, that if you have a family of theories, you could think of that as having a scalar field with values in the parameter space of that theory. So there's a close connection between a single theory, so to speak, with a scalar field, you know, in some manifold, and a family of theories where essentially that scalar field is a constant. But so if the question was, are those ideas incorporated into these axiom systems? The answer is very much, but not usually explicitly talked about. I think in the, yeah, so in one place where it is in work of Stoltz and Teichner, I should say.
I mean, there's a related question. I think actually Nati also asked this question at the strings conference several years ago, which is that if you are given two quantum field theory with the same general, and you specify generalized global symmetry, and let's say the two quantum field theory have the same generalized global symmetry and the same anomaly, then can the two quantum field theory be deformed into each other by a relevant deformation, by some exactly marginal deformation, by turning a parameter while preserving the symmetry? And I don't think there's a general answer to this question. I mean, there are many examples, but and even some counter examples, I think, in 2D, but I don't really, I think it's an interesting question. I don't really know what's the status so far. I think many people are thinking about it. Nati, do you want to say more?
I wanted to ask you about the counter example. What is it?
I thought in 2D 0,1, okay, maybe I don't remember the status of them, but in 2D 0,1, there might be additional obstruction to such deformation based on the topological modular form conjecture.
Yeah,
I'm not an expert, so I cannot say any more. But
yeah, I remember there was something like that, but I don't think it was that clean.
Yeah, I don't know.
I wanted also to slightly clarify something you said.
Mm-hmm.
The question was not whether we could move with relevant or exactly exactly marginal or marginally relevant deformations, but we can also allow embedding it in a bigger theory with more stuff,
right,
and moving that bigger theory. That was the statement. In fact, we have a lot of examples where we really need to throw in more degrees of freedom and move in the bigger space. And from the high energy point of view, this way of thinking about it sounds strange, because why would you like to change if the theory is formulated in the UV? It's like going back to the UV and changing it. But from the condensed matter point of view, not only is it natural, this is what is often being done. And so this is one of the things I really learned from the condensed matter people, that to allow all possible changes at the UV is a way of characterizing deformations of the theory. So when Dan said earlier, kind of interpolating from point to point and staying within the same phase, this is a broader notion of a deformation where you are allowed to go through phase transitions, but there's still some chunks of field space that you will cover and some chunks that you will not. And I have no idea whether this idea is correct or not, and whether it's useful.
I mean, one comment is the following, right? So one consequence of this statement is that take any 3D TQFT, maybe with some appropriate adjectives, you will expect that there's some kind of boundary condition. The reason is because in 3D TQFT, there's no gravitational anomaly. And by boundary condition here, I don't mean topological or gap boundary. I mean general boundary. It could be conformal boundary condition of the Chern-Simons theory. So the question is, does every 3D TQFT emit possibly conformal boundary condition? And I don't think that is, no, maybe then you can correct me if I'm wrong, but it's actually related. In 2D, it's easy. 2D TQFT, right? It's kind of obvious because you can take any, you can organize your local operator into the Cardi state.
It's semi-simple.
It's sorry. That's why I said I omitted a lot of adjectives. Yeah, I want to add semi-simple. But in 3D, it's kind of related to the other statement that every TQFT is in the same width class as a Chern-Simons theory. Right? If that were true, then the statement of having a conformal boundary is also true, because you take any TQFT emits a topological interface with the Chern-Simons theory, and the Chern-Simons theory has a conformal boundary. So anyways, I just want to
don't fully understand the premise of this discussion, because there are many theories that you cannot put a boundary. For example, the chiral boson.
Yeah, but they have a gravitational anomaly. They have gravitational anomaly.
So you say consider theories without gravitation.
I mean, three-dimensional TQFT, and yeah, there's no gravitational anomaly. Again, I'm omitting a lot of adjectives.
So, but I don't, okay, let's assume that you can or cannot. I don't see the relation between this and the other question.
Because if there's no gravitational anomaly, then it's in the same deformation class as the trivial theory. Then that means there must be a deformation connecting that 3D TQFT to a trivially gap face. And you can shrink that deformation into an interface, and that becomes a boundary condition of the 3D TQFT. So a consequence of that conjecture or statement is that every 3D TQFT emits a boundary condition, which I think is not an obvious fact.
Are there counterexamples?
No. Every Chern-Simons gauge theory has a conformal boundary, so that checks out. So one has to ask, what are the 3D TQFTs that are not Chern-Simons gauge theories? And if I recall correctly, almost exactly a year ago, we have such a discussion also at the panel discussion at the Simons Center.
Yeah, and I think I was also at the asking end of this.
That's right.
Yeah, and this is based on a conjecture that Greg and I made before most of you guys were born.
That's right. And then we received some emails from Telemann. But anyways, I think the conjecture in math is that every 3D TQFT shares a topological interface with a Chern-Simons gauge theory. Oh, sorry, sorry. I thought originally they say every, okay, anyways, let me not get into that. Yeah, it's the conjecture, by you guys and also later formulated by mathematician is that, and if you accept that conjecture, then indeed every 3D TQFT emits a boundary condition. So all I was saying is that even in the case of
I'm actually puzzled by what you just said, because let's go back to Dan's question. So we have a TQFT, and we consider it on a manifold with a boundary in order to consider the state that it creates in the Hilbert space. Isn't that a boundary condition?
That's not a boundary condition. That's a cut giving you a Hilbert space. That's not a physical boundary condition.
No, but pick a canonical state in the Hilbert space and just glue it and get it as a boundary condition. Pick a choice state in the Hilbert space and just consider the tensor product.
No, but then you can ask the same question in chiral CFD, where you just said 1 minute ago that there cannot be a boundary condition.
Yeah, because you have to reverse the orientation of the other one. That's why it doesn't work for the chiral one.
But that's true for any theory with a gravitational anomaly. You just cannot cut
it. That's right. So that's why you cannot do it. You cannot use it in the theory with a gravitational anomaly.
Right.
So any theory with a gravitational anomaly is not going to give a counterexample to that.
Right. But in 3D TQFT, I don't understand your construction of the boundary.
Okay, I shouldn't be talking. This is your This is your panel. You should give answers. I should only ask questions.
John has a comment or a question.
Yeah, I was just wondering whether the discussion that just happened offers a way to fix the non-equivalence relation that Shu-Heng was talking about.
Yeah, I think so too. I think the equivalence relation can be made precise by allowing by working modular topological interfaces.
Yeah, but I wonder whether there's a issue that some three-dimensional TQFT can only have a gapless boundary to trivial phase. Or do you mean there's a, when you say boundary, do you mean gapped boundary? I think this adiabatic deformation means the gap boundary, but I think there are examples of three-dimensional anomaly-free TQFT which only allow gapless boundary.
Oh, absolutely, right. So chiral central charge is an obstruction to gap
boundary. No, even chiral charge equal to 0.
That's also true because there are some higher obstruction.
Yeah, exactly.
Yeah. So U1 level 2 times U1 level -4 is one such example. That discussing, like Michael discussed this example too. Yeah, but when in the previous discussion, I also consider conformal boundary, namely gapless boundary as well.
Okay, yeah. So I include gapless boundary. Yeah, thank you.
Yeah.
I'd like to ask one brief question, if that's okay. I can't really help asking this. I mean, Shu-Heng to some extent already answered this in private communication, but it's about axiom systems for quantum gravity, in which, for example, well, first of all, any thoughts? I mean, you might say in gravity one should sum over Bordisms. Is there any way to understand this in terms of the absence of categorical symmetries in gravity? And I know, Shu-Heng, you had some thoughts about that. And I also wonder whether Dan has thoughts about this question.
Dan has no thoughts about this question.
Oh.
No, I've always been mystified by what quantum gravity is. And I mean, way back in '92, I think there was a paper by Witten that led to his conjecture about KDV that Conceived solved and so on. And he wrote down some kinds of axioms, I think, in two-dimensional quantum gravity. But no, I don't have any coherent thoughts, really.
Well, the comment, I think, the thing I discussed with Yale before is just that I think the modern Euclidean way of defining a generalized symmetry in a relativistic quantum field theory is that we have a topological defect, and we can insert the topological defects by wrapping it around some cycles in our Euclidean manifold. And we try to ask how the correlation functions depend on the choice of the defects and the choice of the cycles. But in quantum gravity, we have to sum over topology. So given that we are summing over topology, there's no fixed cycles for us to wrap the topological defects around. So I'm just puzzled by how to even define quantum gravity, generalized symmetry in quantum gravity in the first place. In fact, I think Luca in the audience wrote a paper related to this observation.
All right, thanks. Yeah, we can continue if, all right, go ahead.
I have one more question. I saw here Bowen had something else.
I have a question for Shu-Heng. So lines and surfaces, those are yes, submanifold are of some importance in your talk. So those are for either higher form symmetry or the defects, I guess. So my question is, are those like a manifold structure, or is it more flexible, like some broader sense which may not be manifold, like a part of it is one less dimension, part of it is a two less dimension, or maybe there's something, some part of it is not part of the manifold. Yeah, if the answer is well, we want to restrict to manifold. What's the reason? If not, have you found interesting examples?
So I think outside the relativistic quantum field theory world, there are definitely generalized symmetries associated with locus in space-time that are not manifolds. In fact, I think this morning we heard a very nice talk by Pranay, where it's a lattice model there, but the symmetry is supported on some very funny set of vertices on the lattice, and there's no sense that in any continuum limit that will become a manifold. So in a lot of the fractal world, like the symmetry can be on a fractal geometry on the lattice, and there isn't a continuum manifold limit. Now, in the world of relativistic quantum field theory, you can ask, can you put the defects, put the topological defects on say something that's not quite a manifold, say the intersection between two planes or some intersection between manifolds. Then so that there's a cross or something like that. But then at the intersection, there are more data you have to specify. And there's a whole network of data. You can always insert additional lower dimensional defects along the intersection.
We seem to be at half an hour over already, so unless somebody has some urgent questions, I would suggest we thank our panelists a lot for this really interesting discussion and then take it offline and have like the in-person people have the advantage to pop the panelists some more and say goodbye to the Zoom audience. Oh yeah, what do you say?
Yeah, absolutely. Thank you both. Thanks a lot.
All right, thank you.
Thanks everyone for all the discussion and questions. Thank you.
So Andreas, I guess I'll see you tomorrow.
Yeah, sounds good. I'm about to stop.